Welcome to section 5.1 in Math 95. We're going to be talking about exponents today. We have several rules that we need to develop, and then we are going to use those rules to simplify expressions with exponents. First, a little bit of vocabulary. To start with, we need to know what an exponent is, and you've probably known this for quite a while. But exponents are a shorthand way of writing repeated multiplication. So for instance, something like this. Before we can talk about the repeated multiplication, we need to talk about the pieces present within this expression. X is what we call the base, and 4 is the exponent or power. And overall, x to the 4th means x times x times x times x. So x times itself 4 times. The exponent tells you how many times you multiply the base by itself. So if I look at something like 5 to the 3rd times 5 to the 4th, this is a way of writing repeatedly 5 times 5 times 5, and then 5 times 5 times 5 times 5. So when I'm multiplying, it turns out that I don't actually need the parentheses that I've written there. I wrote them there for a reason, but now I'm going to drop them away. I wrote the parentheses in the first place to show the grouping of 5 to the 3rd and 5 to the 4th. But when I'm multiplying, I don't need them, because I multiply everything all together. So if I would like to write this in exponential form, all I have to do is count my 5s. 1, 2, 3, 4, 5, 6, 7. This winds up being 5 to the 7th. But I could have gotten that just from the original expression I was given. 5 to the 3rd times 5 to the 4th. So to see what's going on there, I want to look at what happens. How do I take a 3 and a 4 and get a 7? I add them. So I could have written my 5 to the 3rd times 5 to the 4th as 5 to the 3 plus 4. And that's what gives us 5 to the 7th. Similarly, if I'm dealing with variables instead of numbers, x squared times x to the 3rd. Here's my x squared. Here's my x to the 3rd. When all is said and done, I have x to the 5th there, which is the same as x to the 2 plus 3. So your book has a way of writing this. It calls it the product rule for exponents. I'm just going to drag this up here so it's with everything else. If m and n are positive integers, meaning whole numbers, and a is a real number, then if I multiply a times n, a to the m times a to the n, I wind up adding the exponents. The shorthand way to think about this is to multiply two powers with the same base, add their exponents. Multiplication turns into addition. So let's practice this. You will be able to do many of these in your head. I strongly, strongly encourage that you show your instructor the step that you're doing in your head. So I could look at this and know that 2 plus 6 is 8, this is 5 to the 8th. But to receive full credit and to show everything that I'm thinking, I would like you to rewrite this as 5 to the 2 plus 6 equals 5 to the 8th. Now 5 to the 8th is a very, very large number, so I'm going to leave it as 5 to the 8th. This is a very large number. So we're not actually going to evaluate that entire number. On a previous slide, we could have tried to evaluate 5 to the 7th, but I'd like to just leave it as 5 to the 7th. So moving forward, this 5 to the 8th is my final answer. With x to the 5th times x to the 9th. Again, I know you can add those two numbers in your head, but I would really like you to show x to the 5 plus 9, which is then x to the 14th. And that would be the final answer. To do this next one, there's a little trick we need to use. We need to write in the exponent of the y that doesn't have 1 written. It's a 1. Anytime you don't see an exponent, the exponent is actually a 1. So now I can write this as y to the 1 plus 4 plus 3, which gives me a y to the 8th. And that's my final answer. Scrolling down just a little bit, things are going to get a little bit more complicated, and that's why I have this hint written here. Only simplify one thing at a time, and show every step. That's this part right here. You'll make fewer mistakes. So when I say only simplify one thing at a time, that might mean that we need to reorder things. So for this case, I'm going to group my numbers together, and then my y's together. And then I can do my multiplications individually. 7 times 6 is 42, not 47. This is why we show our work. I could give you most credit if you had done that. And then I'm going to remind myself that this y has an exponent of 1, so this turns into a y to the 5 plus 1. So finally, I have 42y to the 6th as a final answer. For this last problem, I'm going to use a similar strategy, except now I have 3 bases, so I'm going to break this into 3 pieces. I'm going to have my negative 3 times 5, my x to the 2nd times x, and I'm going to write its 1 there. We like to call that a ninja 1. Not everyone, but several of us at Linn-Benton Community College like to call that a ninja 1. And then I'm going to group my y's together, y to the 7th times y to the 6th. And now I can do my multiplication. Negative 3 times 5 is a negative 15. X to the 2 plus 1. Y to the 7 plus 6. And I'm left with a negative 15. X to the 3rd. Y to the 13th. So that's the product rule. If your bases match, you keep the base and add the exponents. We have another rule to discover. So what if instead I had two things that were divided, same base, but I'm dividing them? So we're going to develop this rule. 2 times 2 times 2 times 2. There's my 2 to the 4th. And then 2 times 2 times 2. There's my 2 to the 3rd. I'm going to make use of the fact that I can simplify fractions here to show what's going to happen with these exponents. So these two 2's will cancel with each other. These two 2's will cancel with each other. And these two 2's cancel with each other, leaving me with a 2 to the 1st power. I'm writing that exponent there to show something specific. How do I go from a 4 and a 3 to get a 1? Subtract. So the way I could show this is 2 to the 4 minus 3 gives me a 2 to the 1st power. Similarly, with variables instead of with numbers, I could write x times x times x times x over x times x. And then, once again, lovely fraction rules tell me I can cancel those two and those two, leaving me with an x squared on top. So x to the 4 minus 2 leaves me with x squared. Very similar to the product rule for exponents, the quotient rule says if I have a non-zero base with m and n being whole numbers, then when I divide them, I'm really subtracting my exponents. Let's practice that a little bit. Again, the work that I would like to see would be y to the 8 minus 2 equals y to the 6th. It doesn't take you very long to do that middle step, and it assures your instructor that you know exactly what's going on with those operators. This would be 6 to the 10 minus 2, which is 6 to the 8th power. Again, this is a very, very large number, so I'm going to leave it as 6 to the 8th. You could plug that into your calculator, and you would get something above 1,000,000, and we're not interested in seeing the numerical value for something that large. What we're interested in is seeing if you know how to manipulate the exponents. So I actually want to move these two up so they're on the same slide. There we go. So just like with multiplying, sometimes it's helpful to break these division problems into smaller pieces. So I'm going to group my numbers together, 36 over 9, and then I have an x to the 5th over x. This 36 over 9 you can know automatically is a 4, but this one I would like to see, this is x to the 5 minus 1, which gives me a 4. I started writing my x, a 4x to the 4th as a final answer. Again, similarly with this next problem, group my numbers together to simplify, group my a's together, and then group my b's together. Give myself a little bit more room to work here. 10 over 15. If you know your fractions well, you know that reduces to 2/3. And then I have an a to the 7 minus 5. And then something over itself is just 1. So I wind up with 2a squared over 3. Now, I know some of you are saying, wait a minute. You went way too fast with that b to the 9th over b to the 9th equaling 1. We are going to see this on the next slide, so just bear with me for one moment. Let me box my final answers here so you can see what we did. And now I'm going to move on to the next slide. Nope, this is going to move me to the previous slide. Nope, it worked. Alright. So I'll revisit that b to the 9th over b to the 9th. But first I want to deal with a smaller exponent than that. X to the 4th over x to the 4th. This is going to be x times x times x times x all over the exact same thing. X times x times x times x. Now you may say this is ridiculous, why are you writing them all out? Well, I do want to show that every single pairing of them cancels, leaving me with 1. You have been doing thing over itself equals 1 for so long that that feels pretty comfortable to you. But what about with exponents? My division rule for exponents said if I have x to the 4th over x to the 4th, I have to subtract my exponents. Well, what exponent does that leave me with? It leaves me with a 0. But we already know that that has to equal 1. So x to the 0 power immediately turns into a 1. I don't care what else is going on, anything to the 0 power is going to turn into a 1. We could do the same thing over here. This is why we come up with shortcuts. Cancel, 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 cancel. 1. This was b to the 9 minus 9 is b to the 0, which we just said has to equal 1. We have just come up with the absolute best exponent rule. And I just made it fly away. As long as a doesn't equal 0. Which, we're in Math 95, I'm not going to throw that at you. Anything to the 0 power automatically equals 1. Let's see how well we do with this. So if I have 8 to the 0, what should I get? 1. Yes. Let me just move these up a little bit. If I have a negative 8 to the 0, what do I have? Do I have 1? Well, be careful with your order of operations. This means do negative 8 to the 0, which is negative 1, which is negative 1. Order of operations says do the exponent first and then the multiplication, and a negative sign sitting out in front of this little expression is actually a multiplication by a negative 1. So be very, very, very careful with this type of thing, but the 8 to the 0 part does equal 1. So now that we've had the rule about order of operations, we've had that conversation, what about 5 times x to the 0? This part right here equals 1, so I'm left with a 5. Okay, but now if you have a y minus 3 all to the 0, that 0 applies to whatever this ends up being. So that gives me a 1. Let me tell you what it isn't. This is not y to the 0 minus 3 to the 0 equals 1 minus 1 equals 0. I don't know what just happened there. That's not true. So that's why it was in the disappearing ink. Oh, it turns into what? Okay, I have to try that one more time, because that's pretty awesome. Apparently this turns into like a flashlight, and I've never known that before. Learn something new every day. Anyway, I digress. This 0 does not distribute to these two, but the entire set inside the parentheses does turn into a 1 because the 0 is all the way outside the parentheses. Check in on time. We're at 18 minutes. I think it's time that we take a break. I did go through several of these rules, so I will go through the next few on the next video. I hope it wasn't too overwhelming. Alright.